Welcome to the last video in this discussion of exponential functions and equations. And in this video, we are going to be discussing how do we actually use exponential growth and decay? How do we actually use models that are exponential in their characteristics, or how do we create the models and use them to make predictions? So let's check out this example. All right, so again, when you see words in math, that's when math becomes real. That is why we learn math, is to actually apply it. So I would suggest slowing down, reading through the problem, and then using your critical thinking skills to kind of solve the problem that's posed to you. So, with that being said, I'm going to go ahead and read this problem to you, and you're going to read along, right? So, medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. This risk is modeled by R is equal to 6 times e raised to the 12.77x, where x represents the blood alcohol concentration and R is the risk of having a car accident, and that risk is given as a percent. You are considered legally drunk if your BAC is 0.08. So 3 questions are being asked. The first question is, what is your risk of having a car accident at this level? The second question is, what BAC would cause your risk to increase to 50%? And the third question would be, what BAC would cause your risk to increase to 100%? So you'll notice that as I put this slide together, I kind of color coded a couple things, right? I pointed out that X is being defined as a blood alcohol concentration, and you'll find X as part of the exponent. And R is defined as being the risk of having a car accident, and that's given as a percent. And that's over here, that's what this model is defining. So we're going to use this model that's given to us in order to answer this first question. Okay, so what is your risk? So R will remain our variable of having a car accident if our BAC is 0.08. So remember, BAC is the X value. I'm given what that value should be. So I can go ahead and sub that in. And then all I really have to do is crunch the numbers to find out what my risk is going to be. So using a calculator and making sure that all of this stuff is in the exponent, you would crunch your numbers and get, well, your risk is going to be about 16.67%. So about 1 out of 6. So that doesn't sound like a very good percentage to me. 1 out of 6 is pretty high. If I were thinking about what is a good risk, I would think 1 out of 1,000, right? Or something with a really high denominator. But 1 out of 6 is pretty strong risk. So I would say do not drive if you are considered legally drunk. All right, next example. What BAC would cause your risk to increase to 50%? So going back to our initial model, I am going to this time solve for X, right? Because I am because I'm looking for my BAC, which is X, but I'm given the risk. So I'm going to go ahead and sub in the risk for R. So I have 50 is equal to 6 times e to the 12.77x. and I want to isolate that x. So I'm going to work from the outside in to get to that x. First, I'm going to get rid of the 6, and I would get rid of that 6 by dividing everything by 6. And then I would get rid of the e. Remember what we do to get rid of the e, the base of e? We're going to take a log with the same base, which is known as ln. So ln of both sides, ln of 50 over 6 is equal to ln of e to the 12.77 times x. But we know that that ln of e is a cancellation, and so we would just be left with 12.77x is equal to ln of 25 thirds. And so we can isolate x by dividing both sides by 12.77. So we would take our calculators and crunch this whole expression. The ln of 25 thirds divided by 12.77 would give us the BAC, right? And so our BAC is going to be about 0.17. All right, so at a BAC of 0.08, we have a risk of about 1 in 6. At a BAC of 0.17, I have a risk of about 1 in 2. That's an extremely high risk. All right, so the last question asks, what BAC would cause your risk to increase to 100%? All right, and so this looks an awful lot like the problem we just did. And so let's just think about what would change here. So we're going to be efficient in our math, right? So I'm just going to sub in something different here, right? Instead of 50, I would put 100. And so this would become 100. And 100 over 6, take the ln of that, would be the ln of 50 over 3. And then divide that by 12.77 to get our answer. So instead of doing all this work again, I'm just going to change my calculation to reflect what has changed. And so instead of the ln of 25 thirds divided by 12.77, now I have the ln of 50 thirds divided by 12.77. And that gives me a blood alcohol concentration of 0.22. So really high and nearly impossible to get home during that time. So definitely, guys, if you are using alcohol, I pray that you use it responsibly, have a DD, or use an Uber, or don't drink. All right, so next example. Here is a new example. We've got the function a is equal to a naught times e to the negative 0.00693x models the amount of pounds of a specific radioactive substance that's stored in a concrete vault x years after it was placed there. If 300 pounds are initially placed in the vault, how many pounds remain 90 years later? Okay, so we are going to use this function and we're going to sub in what we know. Remember that this right here before the e, this is our initial value. A naught always represents the initial value. So what goes there? What's initially placed in the vault? That would be 300 pounds right there, right? And x years after it was placed there, that will be the number of years that have elapsed. So 90 years. So 90 would go here in the x place. So in this case, all we have to do is crunch numbers. I don't have to really solve for anything because all of my variables on the right-hand side have been replaced by values, and I can just use my calculator to crunch this. And when I crunch this, I should get about 160.8 pounds remains after 90 years. Okay, and so this is a real life application of exponential functions. When we have radioactive substances with half-lives, we definitely see exponential functions being modeled there. All right, population growth is another type of common use of exponential functions. And I pulled this data from Google today, and they're real numbers. Let's go ahead and read this through. In the year 2000, the population of the state of Georgia was 7.94 million. And by 2018, it had grown to 10.52 million. Use the exponential growth model below, in which t represents the number of years after 2000, to find the exponential growth function that models this data. Then, estimate the year by which Georgia's population will reach 15 million people. Okay, so this is actually a two-step problem because you see in this model, I have my accumulated population here, my initial population here. K is representing my growth factor. Okay, so if K is positive, we have something that's growing exponentially. And if K is negative, we have something that is decaying exponentially. And then T, of course, will be time. So, to find the exponential function, we need to know the growth factor. And so I don't know what the growth factor is, but I can solve for this by using the two population values that I've got and the elapsed time, okay? Because the time between 2000 and 2018 we know to be 18 years. So I can go ahead and sub those values into that model and then solve for K. So again, we're going to isolate K by working our way from the outside into K, eliminating piece by piece what's going on. So let's go ahead and get rid of the 7.94 by dividing it out. And then let's get rid of the E by taking the ln of both sides. And that really means that the ln of E is gone. We just have the 18K on the right. And then let's get rid of the 18 by taking that natural log of 10.52 divided by 7.94 and dividing that whole thing by 18. Now we can go ahead and then approximate what our K value is, which is our growth factor. So K is approximately 0.01563. So now I know my growth factor, right? And I know my initial population value. And I want to know the year in which Georgia's population is going to reach it. So we can write the exponential function by just subbing in the things that we know now, right? So we know our initial population is 7.94 million. We know our growth factor to be 0.01563. And then T just represents the variable, the time that we're going to sub in, right? So that's our growth function. Then we will use that growth function and set it equal to 15 million, which will allow us to solve for T. So we just sub in that 15 for our accumulated value. And then we can solve for T by eliminating all the stuff, right? So first we would divide by 7.94. And then we would take an ln of both sides. And then we would divide that whole thing by 0.01563. So our T value is about 40.7 years. So remember, this says estimate the year And T represents what? T represents the number of years after 2000. So 40.7 years after 2000. So we could say that that's in the year 2041. Okay, so that wraps up that example. We got one more example, and you knew that if I was doing exponential functions, I could not forget about our current situation, right? And I know this will date this video, but it's okay. Here is an example. Here's a graph that shows the actual numbers of COVID-19 cases in Gwinnett County, okay? And the dates where they were. Okay, so this is in the year 2020, and these are actual data that I pulled. This is actual data pulled from the Georgia Department of Health. Okay, and so we're going to use a graphing calculator and exponential regression to find an equation for exponential growth that models this data. So we're going to use a calculator and let that determine the function for us, and then use that function to make a prediction. Okay, so let's go ahead and look at this. The first thing that you need to do is create a table of the data. Okay, so one column of your data is going to represent the number of days since, this is day 1, so since March 12th. And then the second column in your data will represent the number of COVID-19 cases that have been reported in Gwinnett County. So I've gone ahead and created this table and labeled it with our appropriate labels. Definitely put in the appropriate values here. And then we're going to use some kind of graphing utility to plot these points on a graph. Now, so if you're using a TI product, you're going to put these values in L1 and L2. And then you can look at a scatter plot of the data. Now I use Desmos just because it's easier for me to take pictures of what I'm doing on the computer. And so I used Desmos and I imported the table into Desmos, and it gave me this nice scatter plot of the data. And then we're going to use an exponential regression. You'll find that on your TI, but you can also use Desmos to do regression. So what regression is fitting a curve to the data that we're given. And so you've kind of got to look at the data and decide, well, what kind of function does that most look like? You can make a case for, well, it kind of looks linear. But if you actually drew, a line here, you're kind of missing a lot of the data. This part of the graph kind of shows a curve, right? And so this really kind of does look exponential in its characteristics. And you all have heard that the growth of this virus is exponential. So we're going to use an exponential regression, and we're going to use a times b to the x as our regression equation. And so when you put that in your technology, you're going to get this curve that it looks pretty darn close to the curve of the data. And your technology will be able to then identify what is A and what is B, and y equals a times b raised to the x. And it ends up that this is our function. All right, so that takes care of the exponential growth function, and now let's use it to predict when the number of cases of COVID-19 in Gwinnett County will reach 1,000. Okay, and so this is our accumulated value, right, on this side. So we're going to plug in a 1,000 here. And then we're going to solve for x by getting rid of all this stuff, right? Get rid of the 3.75 by dividing it out. Now get rid of this 1.24, and I'm going to just take a log of 1.24 on both sides. And that gets rid of the right-hand side besides the x. And so x would equal the log of this quotient divided by the log of 1.24. And when I crunch this in my calculator, I get a result of about 26 days. So if I look at what's going on here, this March 30th is day 18. And so 8 days after March 30th will be about April 7th. Now, do we know that that's true? We don't know. We just know that this is a mathematical model to help us make predictions. So it will be interesting when April 7th comes around if we're right on or if we've been able to flatten the curve. Okay, so this is why we want to flatten the curve, right? Because if we flatten this curve out, that means the growth is going to slow down. And that's the whole idea behind this social distancing and quarantine. All right, young men and ladies, it's been a pleasure, and we will see you next time.